Okay, hi everyone. So, this time we're going for C1 indefinite integration. So we haven't moved on to the C2 one yet. Uh, we're just going to do the C1 part. And essentially, what is integration for? What's it used for? What does it mean? Well, calculus, remember we talked about calculus. I don't know if you do remember what calculus meant. Remember that was the Greek word for pebble. And it was called that because they would use pebbles to vote by dropping the number of pebbles, like a white pebble for voting for a certain thing, black pebble voting for another thing, and they would count them all up, and that's how many, that's how democracy started. And obviously the one with the most pebbles won. Now, calculus came under two branches. One of them is differentiation, which we've already covered in a number of ways. In fact, this is a good thing to do then. So differentiation went under, well, what did it do for us? So it found tangents of curves at a point. We used it to find stationary points and classify them. And then we also used it for optimization as well, didn't we? But calculus also includes what's called integration. Now, the fundamental theorem of calculus, that's the first thing that you would learn in your first year studying maths at degree, literally describes integration in two ways. The first way is that it describes it as the opposite of differentiation. That sounds really simplistic, but that is exactly what integration is, the opposite of differentiation. The second function it has is that it can find the areas under curves, and that is your C2 area, and they're going to have some really good math challenges on that. And C1 is your opposite of differentiation. So that's what we're working on at the moment. So if we started with this function here, so if we started with a derivative, dy by dx equals x cubed plus x squared plus 1 and a plus x plus 1, we're starting with a rate of change, aren't we? That's what we're starting with. And the question is, what's the original curve? At the moment, this in itself is a graph, isn't it? And the graph, you can see it's a cubic. The graph looks like this. That's the graph of dy by dx. So this is your dy by dx graph. And this is our x cubed plus x squared plus x plus 1. The question is, what was y? What did y start as? Well, if integration is literally the opposite of differentiation, you know that for differentiation, if y equals ax to the n, the power came down, didn't it? And then we subtracted 1 from the power. So wouldn't it make sense then, if integration is the opposite of differentiation, to do it in the reverse order? So if we start with dy by dx, yeah, equals ax to the n, rather than taking 1 from the power, so bringing the power down and then taking 1 from the power, we would say the integral then of this thing with respect to x. So this is what this notation means. So let's go back. Let's go back. So this is differentiation, but now integration. So integration, starting with ax to the n. So here's an example, isn't it? A is 1 and n is 3. Then y, it would make sense that if you integrate it, you're going to do the opposite to what you did before. So instead of minusing 1 from the power, we would add 1 to the power. And instead of timesing the power down, we would divide by that new power. Can you see? So integration plus 1 to the power, divide by a new power. And we can test it, can't we? We can test this by differentiating it again. So we have a over n plus 1, they're just constants. And now we've got this x to the n plus 1, so the power comes down, x, and take 1 from the power, cancel cancels. Do we get what we started with? Yes, we get what we started with. Now that was a very informal way of me writing this down, so let's do the formal way, the most important way, the notation way. So for integration, we're saying if y equals, or dy by dx equals, it doesn't matter because remember this in itself is a function of its own. I could call that z now, or x now, or t now, do you see? So if y equals ax to the n, then the integral of y, and that's what this symbol here means. This is sigma, much like the Greek countable sum sigma, which looks like that. This elongated s means the uncountable sum. So we're going to talk about this more when we introduce C2 integration. I don't want to focus too much on it, but this one here is called the countable sum, i.e., as before, numbers went from 1 to n in steps of integers, didn't it? So 1, 2, 3, 4, all the way up to n. But for this one, the elongated S1, it's not integers, it's all numbers in between. So 1, 1.1, 1.0001. Do you see what I mean? So it's called the uncountable sum. So the notation for this is you are integrating the curve along the y-axis. So having the sigma, having the elongated s without the dx makes literally no sense, because what are you integrating? What's your variable of interest? So if I do something to the left, I've got to do it to the right. So what I get is the integral of y dx equals, and we just said our new formula, ax to the n plus 1 divided by n plus 1. So add 1 to the power, divide by new power, but we're not quite finished yet, because we haven't considered something, have we? We have not considered something. Let's go back to our curve that we were working on before. Whoops. So this curve here, rub all this out. Okay, so we had dy by dx is x cubed plus x squared plus x plus 1. I'm saying then that if we integrate both sides with respect to x, so remember the sigma with the variable, if you do it to the left, you must do it to the right, bracket, bracket. Okay? That's how you would formally notate this. So you're returning from the gradient to the gradient function. So can you see that your dx and dx basically cancel by a fraction? They are not fractions, and I hope you're not getting too lost on this. But basically, if you integrate dy by dx, you just return to y. And the reason why is because the dx by dx kind of cancel. They're not actually fractions in technical maths, but you can look at them like fractions for now. And you're left with 1 dy. Do you see that? And then on the right hand side, you've still got your x plus 1. And now the variables match. So x's are with x's, y's are with y. So 1 would integrate with respect to y. Remember, ax to the n goes to, when you integrate it, ax to the n plus 1 over n plus 1. So if you've literally just got 1 is your a, x to the 0, that's what 1 is, isn't it? Plus 1 to the power is 1 divided by 1, and you're left with x. So we started with y's, so we're going to do it with y. So that's where the y came from. And now we can start working on this problem. So y equals x cubed plus 1 to the power divided by a new power. X squared plus 1 to the power divided by a new power. X goes to x squared plus 1 to the power divided by new power. That's 1x to the 0, just like we've done. So all constants will just go to that constant, x. Now we're nearly finished, aren't we? But I really hope you're starting to see a problem. What's the problem? Well, let me tell you, because here's what it looks like the solution is. Except we're not quite finished. Because if I integrate and differentiate, that I should be able to get the same answer, shouldn't I? So if I check this, and this is what you should always be doing when you integrate, you should check by differentiating it again. So if I differentiate this, I should get what I started with here, shouldn't I? So x to the 4 over 4, the 4 would come down, that would cancel, and I would be back to x cubed. X to the 3 over 3, the 3 comes down, that cancels, and I am left with x squared. I am left with x, and I am left with 1. Perfect, so it looks like we're all happy then, aren't we? Except no, we're not. We're not happy. Because what if my original function had a plus 3 on the end? If I differentiated it to check, this would be okay, this would be okay, this would be okay, this would be okay, and the plus 3 would disappear to 0. So therefore, yes, I'm happy. But actually, what happens if that was plus? What was if that was plus 2? Or minus 5? Or minus a million? I would still get the same result because constants always differentiate to 0. So can you see, I don't know what my original curve was specifically. I don't know what that plus c is, that y-intercept. So that's why we must have a plus c in there, okay? And this is called your general solution. So a general solution means when you have constants left in the answer, plus c, okay? So if you integrate something and you don't have a plus c, then I've got no interest in your work. You will get minus 1 every time on your exam. I have no interest in your work because you haven't found the curve that I'm looking for. The original curve, I still don't know what the original curve is, do I? So let's just do this again, but we'll formalize it, okay? So all I can offer at the moment is if I integrate both sides with respect to x, we'll do that again, integrate both sides. Remember that notation, very important. The dx both sides, dx cancel. I'm integrating dy, and that's just 1 times dy, isn't it? And now I can do this. So 1 with respect to y matches that variable, so that just gives me y, a quarter x to the 4, a third x to the 3, plus a half x squared plus x, plus c, plus c. This is my general solution, i.e., if I go back to my curve, clear all the ink, if I type in that function, so y equals quarter x to the 4 plus third x to the 3 plus a half x plus x plus c, this is my original curve. But we don't know, just check that, we don't know, look at that, that's a really nice quartic there. But can you see, if I, depending on what the value of c is, that y-intercept changes. I've got a whole family of curves here, a family of curves, alright? That's what it would be described as. How do I get a specific curve? At the moment, my general solution just tells me roughly the shape of the curve, doesn't tell me where it crosses the y-axis, so I can't get a specific curve. The only way to get a specific curve, I hope you're thinking it, is if I gave you a point. If I gave you a point, we can do this. So if I give you a point, let's say the point, so I'm just making this point up. Let's say the point 1, 2. So remember, this is my general solution because it has a plus c in it. I don't know what it is. If the question asks for the particular solution, then this is when must be given a point or some reference in order to know what that is. So particular solution means I must have a point. So solution. And now I can find what plus c is, can't I? If I sub that in. So y is 2 and x is 1. So therefore, I would get 2 equals x is 1, so a quarter plus a third plus a half plus 1 plus c. And if I rearrange to get c equals, I get c equals minus a 12. Okay? So c equals minus a 12, and therefore my yp, so that means particular solution, my finished article is a quarter x to the 4 plus a third x cubed plus a half x squared plus x minus 1 over 12. And that's finished. So you could call this yp, and you could call this yg to signify which solution you found. Now let's do a couple of formal examples then. So here we go. This is the kind of thing that you'd be expected to do. So a curve has been given y equals f of x with a point 90. So straight away, they've given me a point. I know this has got to be something to do with a particular solution, perhaps. And remember, this is C1 at the moment. It's given me an f dash of x. So this is a dy by dx, isn't it? I can't do anything unless it's in the form of ax to the n, because as we know, if y equals ax to the n, if we integrate y with respect to x, we integrate the right-hand side with respect to x, this will equal ax to the n plus 1 over n plus 1 plus c. That's what we need to add to our notes for our formula, because we need to have plus c on there from now on. Again, if you don't have a plus c, I don't know you any longer. Okay? So we've got f dash of x equals x plus 9 over square root of x. It's asking us to find f of x. I can't do that until it's in the form of ax to the n plus bx to the m, right? So that's x over x to the half, exactly more indices stuff, and therefore this is x to the half plus 9x to the minus a half. And now you can start dealing with this thing. So therefore, if I integrate the left with respect to x, I integrate the right with respect to x. Must have that dx on there, very important. So if I started with a dy by dx, that will give me y if I integrate it with respect to x. So f dash of x would just go to f of x. X to the half plus 1 to the power, divide by new power. So fractions coming in here, folks. So minus half plus 1 to the power, divide by new power, plus c. Must have plus c. And now just tidy this up. So that over the fraction flips, doesn't it? So you get 2 by 3 x to the 3 by 2 plus the 2 flips up 18x plus c. So here is my answer to f of x, but it's asking for f of x specifically, and therefore I need the particular solution. So at the moment this is my general solution, so you could write that as g dot s if you like, but I need to know the particular solution. So if we use the point 9, 0, x is 9, y is 0, therefore 0 is 2 by 3 x to the 3 by 2, so 2 by 3, 9, 3 by 2 plus 18, 9 plus c. Therefore c equals, if you rearrange that, so 9 to the 3 by 2 times 2 by 3 plus 18 times 9, 180. So C is minus 180. So therefore, the particular solution is f of x equals 2 by 3 x to the 3... 2 by 3 x to the 3 by 2 plus 18x minus 180. There we go. That's done. Part B, find the x-coordinate of the 2 points on y equals f of x where the gradient of the curve is equal to 10. So be very careful. In C1, they're always mixing up between um, differentiation and integration. As soon as it mentions gradient, we're talking about dy by dx, aren't we? We're talking about when the gradient is equal to 10. So when f dash of x is equal to 10. So f dash of x equals x plus 9 over x to the half equals 10. What are the points where this thing equals 10? So if I times up, I get this. If I move everything over to one side, I get this. Now, I wonder if you can spot this. It's a classic trick that they would use. This can be factorized because the power here is 1, and this power is half of that power. So therefore, I can make this x to the half, x to the half. And what's going to make this 9 and 1 minus and minus? So I know x to the half is 1, x to the half is 9, so therefore x equals 1, squaring both sides, and x equals 81. And there we go. That's the x-coordinates of the 2 points where the gradient is equal to 10. So be really careful about that. Number 2 then, last formal example. So given f dash of x equals this thing, it's giving you a point, so straight away I'm thinking of a particular solution needed. Go a bit quicker this time, find f of x. So we know f dash of x equals, can't do anything with this until it's in ax to the n form. So minus 9 over 4 x to the minus a half. Now I can work with it, plus 2. And if we're going to integrate the left, we have to integrate the right. So good notation. Remember that dx. I don't see a dx. I don't know you anymore. F of x equals, and now 3 over 2 x plus 1 to the power 3 by 2 divide by new power. So leave your numbers on the outside. Minus 9 over 4 x plus 1 to the power divide by new power. Plus 2, the constant, just instantly whack an x next to it. Plus c, must have plus c. And let's tidy this up. So that 3 over 2 on the bottom will flip up and dissolve that 3 over 2. They would cancel out. So x to the 3 by 2. And then the 2 would flip up. So that's minus 9 over 2. X to the half. Plus 2x plus c. And this is f of x here. So here we go. This is our general solution, isn't it? Because it's got a plus c in it still. But we want to find the particular solution at 4, 9. So 0.49. Y is 9. X is 4. And when you rearrange that, you should get, for the sake of speed, remember you will not be allowed to use a calculator. So plus 8, 9. So I get C as 2. Hopefully that's correct and you're following this. So therefore your particular solution, f of x, will be f of x then will be x to the 3 by 2 minus 9 over 2, x to the half plus 2x plus 2. Okay, just put that again. x to the 3 over 2. Okay, so we're happy with that. That's part A done. Part B, it says that the point P lies on the curve. So I called that other point P. Let's not be confused then. Let's call that Q or something. I just made that letter up. Okay, so point P lies on the curve. The normal to the point P is parallel to the line dy 2y plus x equals 0. Find the x coordinate of P. So first, if the normal is parallel, then let's get this in the form of y equals mx plus c, and then we can see what the gradient is that we're talking about. So 2y equals minus x, so y equals minus a half x. So that's the gradient. So grad of normal, remember, is minus a half. So just pause the video and do this by yourself if you think you can do it, and then go back with me, okay? So the normal to the curve at P is parallel to that line. So that means the regular gradient m1 must be minus 1 over that. So the regular gradient must be 2. Remember, we're talking about gradients here. So gradient means that I'm going back to this f dash here. So f dash of x equals 3 over 2 x to the half minus 9 over 4 x to the minus a half plus 2 equals 2. So we're looking at when this thing equals 2. So the 2 and the 2 cancel out, so I'm left with 3 over 2 x to the half minus 9 over 4 x to the minus a half equals 0. Looks nasty, but if we start manipulating this thing, so this is 3 root x over 2 equals 9 over 4 root x, isn't it? Just move that over and sorted my indices out. So if we move all the numbers over, so times by 2, divide by 3, we get root x equals times by 2, that's 9 over 2, divide by 3, so that's 3 over 2 root x. So if I times that by x, root x, sorry, I get x equals 3 over 2. So x equals 3 over 2 at P. Okay, so just realize, folks, so remember this is your particular solution now. That was your general solution. I just realized on the previous example, hopefully you spotted this, that actually when I was rearranging I should have a half here. So that's 18x to the half, so that's a half, and therefore C isn't minus 180. C is actually, if we put that in, again, so 9 to the 3 over 2. Okay, so 2 divided by 3, 9 to the power of 3 by 2, plus 18, and now 9 to the power of 0.5. It's 72, so actually C is minus 72. Sorry about that. So this is minus 72. So hopefully you spotted that and you thought, oh no, there's a mistake there. So that's it for that video then. Hopefully that's integration sorted.